So, good afternoon once again to all of you. Before we went for the midsem exams, we learnt about single stage amplifiers as well as differential amplifiers, but we didn't talk about how these amplifiers would respond at high frequencies. Okay, so all those analysis which we did, we neglected the effect of all the parasitic capacitances. We primarily dealt with an ID, GM equations and R naught and things like that, and all that equations and analysis is true only when the frequencies are lower. At high frequencies, the capacitances also at each of those nodes, they do have a role to play. So we will try and understand how those capacitance affect the performance of the amplifiers. In today's class, we'll talk about a single stage amplifiers. Okay. To start with, just a recap of what an high pass filter is. So if you have a capacitor here, if you have an input voltage signal and you have a resistance here, at low frequencies this capacitance will offer very high impedance, and hence this input signal will not be reflected at the output. However, at very high frequencies the capacitance.
Hello.
Yes, tell me.
Sir, I think recording is not started.
Yeah, okay.
Thank you, sir.
Yeah. So, to start with high pass filters, so at very low frequencies, we have this capacitance, and which blocks the low frequencies. It offers high impedance at low frequencies because the impedance of capacitance is 1 by C omega, right? So at low frequency, that omega is in the denominator, omega is 2 pi f, so it offers high impedance. But at high frequencies, that becomes negligible. Okay. So if I try to write the output voltage and with respect to the input voltage, how would it is like a potential divider. R divided by R plus 1 by j omega c is the capacitance, impedance offered by the capacitance, right? So now if I just try to find out the gain, so I bring the V in out here. Let me increase the size of the pointer. Okay, so now this becomes R divided by R plus j omega, or I can write it as 1 divided by 1 plus j omega RC, right? Now this omega is equal to 1 by RC is known as the critical frequency. Okay, so omega 0 is equal to, so there is a meaning attached to it. We'll see that and what is that. Okay. So now if I write 1 by RC as omega, so this becomes omega. J omega can be written as S also. So this is now again further simplified, S divided by 1 plus divided by S plus omega c. So this particular equation, it has got a pole at minus 1 by RC. Okay, that means when S is equal to minus 1 by RC, so this denominator becomes a 0. Okay. It has at 0 at 0. That means when S is equal to 0, again you have this entire expression going as 0. So that's why we call it, it has got a pole at 1 by RC and 0 at 0. Okay. Now if you consider just the magnitude of this thing, okay, because j omega means there is a phase difference also. So if I just take the magnitude, it will be 1 by omega 0 divided by omega. Okay, from here, if I just talk about the magnitude aspect, so this is the magnitude of the gain, and this is the phase. Okay, because there is a capacitor which has been induced, so there will be a phase also, phase difference also with respect to the input. So this is the gain formula. This is the magnitude, this is the phase. So this is a high pass filter which we learned in our basic electrical science. Okay. Now if you see here, why do we call omega is equal omega 0 as the corner frequency, or we call it as a critical frequency, cutoff frequency, corner frequency? These are the various names which is given to omega 0, represented by 1 by RC, because when omega is equal to omega 0, if you see the magnitude here, okay, this becomes 1. Okay, and hence the gain becomes 1 by root 2. Okay, so the voltage gain magnitude of the voltage gain becomes 1 by root 2, or the power becomes a half of that, because power is V square by R, right? So if the voltage becomes 1 by root 2, power becomes a half. So that is the significance of omega 0, okay, is equal to 1 by RC. At this particular frequency, okay, the power will become 1 by root 2 times. No, power becomes half, okay, from the actual level, right? And this is here in the pass band you have some voltage at around corner frequency, okay, from here to here, okay, the power will become half, okay. So now we also know that the voltages are can be represented in dB as 10 log AV, and the power is represented as 20 log V. So if you consider that the for a voltage of 1 by root 2 voltage gain, okay, where the voltage falls to 1 by root 2, if I put this value out here, it comes out to be 3 dB. So 3 dB is nothing but 3 dB is the is corresponding to 50% power loss, okay. So here I have some power from here to here. So if it is coming 3 dB, that means 50% power loss, okay. So this frequency corresponds to the corner frequency at which from the mid band you will have 3 dB. So for an high pass filter, the input signal is coming as it is, okay, at the output. So it is 0 dB, right? Log 1 is 0, so it is 0 dB. At the corner frequency, it will be minus 3 dB, the power gain, okay. So this is the significance of FC. Similarly, if you see the phase, it starts at 90 and it goes to 0 out here. So here if I put omega is equal to 0, okay, initially it will be tan inverse infinity, which is 90. But when omega is approaching very high frequencies, this tends to 0. So this comes to 0. At corner frequency, it is tan inverse 1. So it is 45 degree. Is these two graphs are clear and things are clear how a high pass filter works? Anybody has got any doubt? We can discuss it again.
Sir, when we are calculating magnitude, so can you go to previous slide?
Yes.
So here J is there. So when we take the magnitude of J, will it not be minus 1?
Yes. So if that is square, right? So it will become an
No, after square it will become minus 1.
No. It is like an a plus x plus ij, right? So that x plus j into y. So x square plus y square root, that is the magnitude. This becomes
okay.
phase.
We are not taking square of j.
No.
Okay.
We are
It's
assuming
polar form.
Polar form. Yeah.
Okay.
Right. So this is the magnitude. Okay. So this is how an high pass response would look like. Right. So similarly, I could have a low pass filter also. So there is a resistor here, capacitor here. So at low, very low frequencies, okay, this will be open circuit. So you will have the entire signal coming. At high frequencies, this will start. This will become a low impedance, and hence there will be a voltage will start getting attenuated. Okay, so this is known as low pass filter. Low pass means low frequencies will be passed. Okay. Now again, if I write the potential divider equation, it is 1 by j omega, this capacitance, and R plus 1 by j omega. Again here also it's the same, corner frequency is given by omega 0 is equal to 1 by RC, and then the gain is written in as 1 by if you take the LCM out here, the j omega c gets cancelled, and this is what you get. And again some taking omega 0 to the top and some rearrangement, you will get this. Okay, so it has got one pole at s divided by omega 0. Again the magnitude of this is again same here, right? So and whereas there is a minus out here, so that is the difference which comes here in the low pass filter. But if I see this plot here, since it's a low pass filter, at low frequencies it will be 0 dB, and at omega is equal to 1 by RC, at the same critical frequency, I will have 3 dB out here. Okay, so I'll have 3 dB less, and then it will go down here, down route here. Okay, now what is the slope of this curve? If you see here, the slope of this curve will be 20 dB per decade. Okay, so 20 that means for every decade, like from 1 hertz to 10 hertz to 100 hertz, when you move, that is 1 decade, right, into 10. So for every 1 decade, okay, there will be a 20 dB loss. Okay, so this is what a single pole does to a transfer function. These are from just from basic electrical. Similarly, here also, if I go back here also, this slope will be 20 dB per decade. Okay, so so this is the slope. So in case somebody wants to know more about low pass and high pass filters, you can go to my course page. There is a course known as Electrical Sciences, in which there is one lesson which is known as passive filters. Okay, so all these how this 20 dB per decade has come, all those derivations have been done there. Okay, so in this class we will just try to understand. This is the corner frequency, after which it will be 20 dB per decade fall. Okay, this is what a low pass filter does to a circuit, to an input signal. So generally an amplifier, okay, it could have it will be a band pass, whereas very low frequencies might be attenuated like this. So you can have any frequencies below W by L, okay, corner frequency, it will have, this will have, see, when I say bandwidth of a filter of a circuit, it means that at WL, that is the lower limit, okay, it will have 3 dB from here to here. Similarly, this is also 3 dB at WH. Okay, so if at all I want to transmit this particular frequency, okay, say 1 kilohertz, so I need to keep this W by L slightly if I have to have 1 kilohertz, if you are making a circuit for 1 kilohertz signal to be passed, and if I make this WL to be 1 kilohertz, you have to remember at 1 kilohertz it will be 3 dB down. Okay, so I might as well try to make it for 100 hertz, so that this is the total mid band gain, the desired frequencies should fall. The desired frequencies should fall here. Okay, you should not try to put your desired frequencies at these limits. Understood? Because these RC values, you will have 3 dB. It is already 3 dB loss out here, right? So your desired frequencies should be within here. So at 3 dBs, you will have to understand that at these frequencies, the power is almost half. Okay, so you have to keep that in mind. Okay, so when you design a circuit, so 1 kilohertz, don't try to put WL at 1 kilohertz, right? So if you keep WL instead of 1 kilohertz, you might want to keep it as 1 decade lower, as 100 hertz. Okay, so that 1 kilohertz falls somewhere here, right? Similarly, if your maximum frequency requirement is say 100 megahertz. Okay, now if you try to design 100 megahertz with WH, so at 100 megahertz you will get the max possible gain, 3 dB down you will get. So you might want to keep it as 1000 megahertz WH, so that 100 megahertz falls here, right? So it is a good practice. So whenever I want to design a circuit, my frequency requirement should fall in the pass band itself, here itself, although this is known as pass band. Theoretically, this is known as the pass band. Okay, but you have to understand this, there will be attenuation in this gap also. So it is better to take 1 decade extra on both the sides. Okay, so that is known as amplifier transfer function. So for each of our different configurations of amplifiers, we will see what are these frequencies, how do these frequencies get restricted. So that analysis we will do it today. Okay, so when we write a transfer function of an amplifier, so there could be this is the standard form. There could be a few zeros and there could be few poles. Okay, so these zeros are generally very far away. Okay, so we should be more bothered about the poles out here. So each of these poles, okay, what they will do is they will start attenuating. So I have the first pole here, it will start. The first pole means which is closest to from the zero side, okay, lowest frequency pole. It will start attenuating here. Now similarly the second pole here, now this pole is also acting, this pole is also acting. So the rate at which the signal deteriorates will be 20 dB per decade. Okay, this is 40 dB per decade. Okay, now the third pole also comes into picture here. Now all these three poles together they start acting, then it will become minus 60 per decade. Okay, so we have to find out for a circuit where are these poles. Okay, now once those poles are known, then we can draw this graph. In many circuits you will have something known as a very dominant pole. Okay, that dominant pole will be at much lower frequencies. Then this itself will go like this, right? So then these are not very relevant, because this is become a dominant pole. So this only is going to restrict my gain. Okay, so these kind of dominant poles also might be there in the circuit. Okay, so you have to take care of those kind of poles also, right? Okay, is it understood till here?
Sir, can you explain the significance of poles and zeros?
Yeah. Okay. So where is this noise coming in from? Okay, I can mute that participant. I'm not able to. Is it from Abhishek? No. Okay. Okay. No, I have already muted him. Okay. So see, every pole, okay, every pole will is a place at which the frequency starts falling at 20 dB per decade. So you add one more pole. So this pole is corresponding to the RC value which you get out here. Okay, this S is equal to P1. So this pole will be decided by the RC value. So there will be several capacitors and resistances in a circuit. Each of those capacitors will contribute towards one pole out here. So those poles will start, all those poles in combination, all of them may not be having the same W0, right? Because W0 is 1 by RC. So in a circuit there could be several capacitances and several resistances. So they will together form a pole, right? And all those poles may not be at the same frequency. They will be at different frequencies. So that pole which comes in the first with the lowermost frequency, that is the one known as the dominant pole. That will start attenuating first, and then after some time the next pole also will start, because this is W01, this is W02. Now from this point onwards, both these poles, both these filters will start acting. So it will, this also will attenuate the signal, this will also attenuate the signal, and hence it will start falling at a higher rate. Okay, so the slope will become 40 dB per decade. Similarly, there could be the third pole which will be coming into the circuit after some time. Then again the slope will increase to 60 dB kind of thing. Is it understood?
Sir, like the previous stage attenuation will be added when we add next stage.
No, no. Like let us take one example of CS amplifier and we'll revisit that. Okay, let's try and understand where are these poles, what do these poles do, and then we'll come back to this slide again. Okay, so I think once we take an example, things will be clear. Okay. So if there is an expression like this, if the transfer function is like this, there could be several poles. Okay, so in case one pole is dominant, then we can write WHS WP1 like this. That is this example in which this pole is very dominant. Okay, So if it is dominant like this, then these are these can be neglected, right? So because this is very this is at a much lower frequency, so this starts affecting the signal very early in the frequency domain. So this becomes a dominant pole. So in that case, we can use this formula. But in case all the poles are close to each other, then we can call this as WH formula. We can use this formula to compute the bandwidth. Okay, this is the bandwidth computation. Okay, so we'll see some examples, then things will be more clear. Okay, now how to compute these poles in a circuit? Okay, so there are several approaches. So the first approach is open circuit time constant method. Okay, so there will be several capacitors. So you take one capacitor at any given time. Okay, and then you remove that capacitor and you put a voltage source there. Okay, you remove that capacitor and you put a voltage source here, and see from here now what all resistances it is seeing. Okay. Yeah. So what all resistances this particular capacitance is seeing. While doing so, you remove all the capacitors and put an open circuit out here, right? So and then you compute the resistance. So that resistance and capacitance will give me one pole. Okay. Similarly, then you keep doing that, and then you find out all the poles which are available. Okay. So with that we can determine what are the different poles available, and then you can find out the bandwidth by doing a summation of all the poles. Okay, so that we can do that, and to find out the mid band gain, you just neglect the effect of the capacitances, and then you find the poles, different poles, and with each pole you start taking the first pole, you take 20 dB, 40 dB, 60 dB, right? So this is how we go about it. So we'll do an example and things will be clear. Okay, so basically what an open circuit time constant method does is, there will be several capacitances in the circuit. Okay, so for each capacitance, okay, you have to find out omega 0 is equal to 1 by RC. So that will be one frequency by that RC combination. Now to find out each capacitance, what is the resistance which is coming in combination with it. Okay, for that what we do is we remove all other capacitors, we put open circuits. Okay, and then at that capacitor which is of interest to us, okay, we put a voltage source there and see what are the resistances which that voltage source is seeing. Okay, from there we compute the equivalent resistance. Okay, so similarly then you go to the next capacitor, then the next capacitor, and you cover all the capacitances in the circuit. Okay, and then for the time constant you do a summation of all the RC values, or for the bandwidth it will be 1 by RC, so summation of all the poles. Okay, so let's see how it is done. So before doing that, there is second method which is known as Miller method. Okay, so why I am covering Miller method out here is, then for each of these circuits we will apply both these techniques and see. Okay, so in Miller theorem what it says is, now suppose this is a node. Okay, this is an amplifier. Suppose there is an amplifier here, it has gotten gain gain K, right? So this is, so now there is an impedance which is available here, need not be capacitor, it could be anything. Okay, so this Y is the impedance which is it is the admittance. Okay, instead of impedance I am calling it as admittance out here. So Y. Okay, so now if you see here I1, okay, is I1 is Y into V1 minus V2. So this is V2. So the current flowing here will be V1 minus V2, because this is the voltage V1, this is the voltage V2. So I V1 minus V2. So if I take V1 out common out here, it will be V2 minus V1, and since the relation between V2 and V1 is defined by the gain K, Okay, so I can write it as K. So this equation becomes like this. Is this two equations clear to all of you? Anybody has got any doubt? Is it okay?
No, sir. No, sir.
No means there is a doubt.
No, no, no doubt.
Okay. Okay. So now these two equations are clear. Now I can represent this circuit like this also. Okay. What is this representation? Instead of having one capacitance, one impedance across this amplifier from here to here, I can put it into the input side here, because this will make it analysis easier. So so that capacitance, like for an CS amplifier, between the gate and the drain, okay, that capacitance, so that is now represented here like this. If I am pushing it down here like this, okay, so it comes here like this, right? So now this is the equivalent circuit. Okay, so in the equivalent circuit also the same current has to flow, right? So now this is in the equivalent circuit. So this is for the equivalent circuit, and this is for the original circuit. So for the equivalent circuit, I can write I1 is equal to Y1 divided by, okay, V1. Now this is Y1. Okay, instead of Y has got transformed to Y1 here. So I can write Y1. So from these two equations, I can write Y1 is equal to Y minus Y into 1 minus K. Okay, or I can write Y1 is approximately equal to Y into K if the gain is high, right? So this is what is the Miller capacitance. This is what we discussed earlier also. We saw those Miller capacitance, right? That gets multiplied by the gain into the input side. So this is what this Y1 is getting multiplied by a factor K. Okay, so this is for admittance. Same happens for, if I just write for the impedance also, it will come. So capacitance is what now? Capacitance impedance is right, and C omega, right? So in case of an capacitance out here, okay, so the new capacitance will be K times, that is the gain, capacitance multiplied by the gain into the input side. Is it okay? Is this okay with all of you?
Yes, sir.
Okay. Now if I take about the output side, okay, then I can write for this is for the first two equations are for the for this circuit. Okay, now for that is for the original circuit. Okay, now I have an I2 is V2 minus an V1 by Y. Okay, so this become Y. If I take common, it will be V2 minus V1 by, so it will become 1 minus 1 by K. Okay, now for this circuit, this is coming from here, okay, from the equivalent circuit, I2 is Y2. So if I equate these two equations, I2 get Y2 is equal to Y minus 1 by K. Okay, what happens, if K is very large, if there is a large gain, then this becomes negligible. So Y2 is approximately equal to Y. So if it is a capacitance out here between the gate, between the input and the output, generally for a CS amplifier it will be gate to drain capacitance. Towards the input side, it will get multiplied by the gain, and the same capacitance gets reflected at the output, but in the output it doesn't get multiplied by the gain. It will just go just like that. Is it okay? Is it okay till here? Yeah, it might be
Yes,
probably a little bit vague out here, but once we see the circuits, it will be clear. So these are the basic two approaches to solve high frequency analysis of circuits. So let's see. So now this is an amplifier. Okay, this was the amplifier initially we saw. So now if you want to make an equivalent circuit out of here, so this is an Vs, this is Rs. Now initially we talked only about Vgs, but at high frequencies, now this is Vgs out here. Okay, and then from here to here we have a CGD. So this is additional capacitance which has come here, VCGS, GMVGS. Okay, this is R0CL. So these are the two capacitances. Okay, there. This is there. This is there. So that has been represented here in this circuit. Okay. Now that circuit can be this CGD. Again, if I want to separate it into two, okay, what I can do is I can cut it from here, and I can put one more capacitance here, right? Capacitance here, and this value will be CGD into GM RL dash. Okay, what is GM RL dash? It is the gain. Correct? Gain. This RL dash is parallel. So you have to this capacitance is going to be CGD into the gain. Gain is nothing but GM RL dash. Similarly, at the output node also there will be one capacitance. Okay, so this capacitor, I am breaking this connection out here. I am dividing it into 2. So this will become simply CGD. Is it okay? So how to make an now the CS amplifier, initially we didn't have these two. Now these two capacitances also gets incorporated into the design. Okay, so the circuit will get modified. Now at high frequencies, and how does the circuit operate at high frequencies? So we need to find out. Okay, so there is several techniques. So let's take the first circuit technique, which is an RC time constant method. Okay, now this is the equivalent circuit. You have CGS. Now we have to find out, okay, what is the resistance seen by this capacitance. Okay, what is the resistance seen by this capacitance? For that, what do? We have to open circuit the other capacitors. So we open circuit, so there is no capacitance here, and we have to put a voltage source out here and see what are the resistances as seen by this test source. Okay, so now when I see from here, okay, I can see only RS. Okay, so I get one pole at RS CS, this time constant. Is this much clear to all of you? Is this an equivalent circuit understood? Yeah?
Yes, sir.
Yeah, okay. This is slightly difficult. Not difficult. It might appear slightly complex, but things are very simple. In case you are not able to follow, please stop me. We can repeat and go slow on it. Okay. Now we get one pole. Now what about the second pole? In the second pole, yeah, tell me.
So that second circuit, how that CGS became VTST and I, that one is not clear.
Okay. See, this is this equivalent circuit clear? CGD and CGS. Okay. Yes. Okay. Now we have to find out, okay, what is the each capacitor will result in one pole. Okay, it will deteriorate the high frequencies, right? When you are giving signal here, high frequencies will be bypassed by this by this capacitance. Okay, and hence the VGS will deteriorate. So we have to find out what is the pole contributed by this capacitance. Okay, for that, okay, the procedure is we take one capacitance at one go. So all the other capacitance in the circuit, in this case there is only two capacitors, all the other capacitance will be open circuited. So I have removed that capacitance, right? And I have to see what is the resistance which will be seen by this capacitance. So I've just put one test circuit and trying to see, okay, what is the resistance which will be seen from this. Okay, what is the resistance which will get paired with this capacitance. So I have put a voltage source out here. Okay, the symbol is of an current source, but it's a voltage source. Okay, which has been put here, right? So I see that the resistance as seen by this capacitance will be only RS, right? So this will give me one pole. Is it okay with all of you till here? Is it okay? Anybody has got any doubts? Okay. Okay. Now I have to find what this capacitance does. What is it seeing? So I make this open circuit. Okay, and I put a voltage source out here. Okay. Now if I have to find out, okay, So, I can write an IST is equal to, okay, first equation. This is the test current. Excuse me. Now, this is the test current, okay, minus VGS by RS, because this is VGS, okay. This is VGS. So, although I have kept it open circuit, but there will be a voltage at this node, right. So, and that voltage will be nothing but I test current into minus VGS RS, okay. So, VGS, because the current now that I have taken the direction of the current in this direction. So, this becomes minus VGS RS. Is this equation clear to all of you? First equation, I test is equal to minus VGS by RS. Is it okay? I am trying to find out what is this capacitance, what kind of resistance is this capacitance C. So, I have removed the other capacitance and I am putting one I test and I am trying to find out, okay. Now, so I get one equation. The second equation is this current is being split into two branches, right, one current here and one current here, right. So, I can write now I test is equal to one current is GM VGS, which is flowing here, okay, and what about the other current? Now, this voltage out here is VGS and the voltage out here, this we have taken as plus minus. So, it will be VGS plus V test voltage, okay. So, the net voltage out here will be that divided by this resistance, okay. So, V out by this. So, V out is nothing but this voltage plus this voltage. So, you write this voltage, right. So, I have this equation and this equation, right. So, if I try to find out from these two equations, V test by IST, okay, here I have VGS, right. So, I am going to substitute this VGS by IST by RS, right, IST by RS, and VGS I am going to again here also I am going to substitute it by IST by RS. So, and then I take VST by V test by I test, okay, that is the resistance as seen by the capacitance. I will get this, okay. Now, this, right, this is the equation which I get, okay. That multiplied by CGD will give me the second pole, okay, that will give me the second pole, okay. So, this is the first pole RS into CGS, the second pole is this, okay, the RL parallel to R0 plus GM. Now, if you see in this equation, okay, this is a very much higher than corresponding to these RL parallel to R0 and RS. So, if I write approximate value, okay, it will be just be GM into, if I just write the approximate value, it will be GM into RS RL parallel to R0, right, into CGD, right. If I just take this term and neglect the other terms, okay. Now, what is this GM into RL R0? That is the gain of the amplifier, right. So, it is the gain, right. So, A into CGD into RS, right. So, what is actually happening, right. So, the second, yeah, why
RS is neglected
here? I am telling because if you consider the middle portion, right, this will be much higher than the first term and the last term. So, I am just taking the second term, in between term,
okay,
right. That is GM into RS, then RL parallel to R0, right. So, GM and RL parallel to R0 is the gain, correct,
right.
So, then what is remaining? RS, right, gain and CGD. That means CGD is getting, so instead of making all these circuits, it is just simple. One is CGS, the other is CGD into the gain, the second capacitor. Is it okay?
Yes.
So, there are two poles in this circuit, right. The first pole is RS CGS, and what is the second pole? The second pole, okay, will be at RS into CGD into gain. Is it okay with all of you? Is it okay? Anybody has got any
Sir,
doubt? Yeah.
Can you explain RGD again?
Yeah, sure. Okay. So let's start. There are two capacitances out here. First, we are trying to find out what is the resistance as seen by CGS. Okay. So we are going to put an voltage source here and a current which is going here as V test and I test, and we are going to open circuit this. So this is open circuited. Now what is, now if I write an equation, okay, here V test is equal to I test into RS. Okay, so V test by R test is RS. So that is the resistance which will be seen by this capacitor. So the first pole will be RS into CGS. Is this much clear to all of you? We talked about this capacitance. So the resistance which will be seen by this capacitance is RS. So CGS. Is it okay?
Yes.
Okay. Now we are trying to find out what happens to CGD. Okay. Now in this case we are keeping this capacitance as open circuit. This capacitance. Okay. Is it understood till here? Now for the second this thing, we are putting a voltage source out here, right? Voltage source out here, and we are open circuiting out here. Okay. Now, so this is the current which is flowing. So one equation is IST is equal to VGS into RS. Is this equation clear to all of you? One equation.
Yeah, it's from the above one.
Yeah, from here.
CGS.
From here, it is coming from here. This is one equation. Again, I am writing an KCL at this node, right? So IST is GMVGS, this current plus this current, okay, which is, this is flowing into this. Okay, now what is the voltage across here? Okay, this is VGS plus VGS is available till here. Another V test is available here. So I am writing VGS plus VTS divided by this resistance. Is it okay till here?
Yes, yes.
Okay. Now here there is an I test here, VGS
Hello?
here. Yes, tell me.
No.
Sir, can you increase the cursor?
How this current?
Yeah. Okay. So
thank you.
yes. So now this is VGS plus and R. This is R0. Now you have here you have one VGS here. So that VGS values is been substituted in these equations as I test into RS. Okay, and a negative sign. So if you do that, then finally you can take these terms here and write V test by I test is the resistance which will be seen by this capacitance. So that comes out to be like this. Is it okay with all of you?
Sir, from where we get the V test value?
No, I am just taking it as a V test. Okay,
Okay, it will
then
cancel out.
yeah, I am just removing that. I am finally taking V test by I test. So both these will get cancelled out. So only these terms will remain.
Okay.
Right? I am just putting a test signal, a voltage and a current, and trying to find out what is the resistance as seen by the capacitance. Is it okay with all of you till here?
Yes.
Okay. Now when we see this, so this is the equation which I get. This is a big equation. Now if I neglect this, okay, this is just the second pole. Okay, one pole is here already. This is about the second pole. So this resistance which we got, I am multiplying it with that capacitance, this capacitance under consideration. So this is CGD here, RGD into CGD. Okay, so because now this test we had applied at this particular position where this capacitance GD was there. So I am multiplying it with CGD to get that pole, okay, with this expression. In this expression has got 1, 2, 3 terms, okay, 1, 2, 3 terms. Now in these 3 terms, the middle term will be much higher than the first term and the last term. So if I just consider the middle term, okay, then the whole expression will reduce to Gm into Rs, RL parallel to R0 and CGD, okay. Now what is Gm into RL parallel to R0? That is the gain, okay. So now it will become Rs into gain into CGD. So gain into CGD. So that means if you look at other way around, then it is just the gain into CGD into Rs. Is it okay? The same thing we'll get by doing a Miller. Okay. Now if you, this is what it is, summing up. Then finally omega, the highest frequency this amplifier can support will be given by this pole and this pole together. Okay. So this is the final high frequency. At this frequency, the gain will drop to 3 dB. That is, the magnitude will fall by 1 by root 2 and the power will fall to 1 by 2. So that frequency will be given by this particular equation. Is it okay with all of you till here?
Sir, in the previous slide, that RGD calculation, where so I tried this equation by putting I test value in this, but I'm not getting the value that you written here. Like VTST is still as a variable. So how to replace that thing? What I did is just I took 1 upon RGD.
This is VGS, right? Right?
Correct.
So this VGS will be replaced as I test into RS into GM.
Okay.
Right? So there is no V, so this will come here. Okay, you can. Similarly, what about this VGS? This VGS is going to be replaced as I test into RS again. Right? So this VTS, this also will vanish. This will also you will get in terms of I test. So that also you will get to the left hand side. On the right hand side, only this much will remain.
Okay.
Right?
Yeah, sir, got it.
And then you divide this. Okay, you will get it.
Yeah.
Okay.
Yeah.
Right? So instead of doing all those things, okay, we can straight away come to the solution by using Miller theorem. Okay, what we have an CGD. Okay, so we just represent that CGD here. Okay, so this will become 1 plus GM into gain into 1 plus GM. If you see the Miller, it was 1 plus K, right? And 1 minus K it is. Here the gain is minus GMRLD, right? So this will become, because the gain of a CS amplifier is negative, right? So this will become 1 plus GM into RL. So this is the capacitance out here, right? So this is the capacitance out here. So again that will be get reflected at the output side also as GD, directly GD, okay? Whereas the input side it will get as 1 plus GM into RL dash, or even you can neglect this M also, right? Then straight away you can write these two capacitances are in parallel, so they just add up. So CGS plus CGD into 1 plus GM RL dash, which is the gain into CGD, okay? 1 plus gain into CGD into RS. So this circuit becomes, so this high frequency response can be directly found out by using Miller theorem. Okay, here we did a very involved calculations, but without that also straight away we can get to this result. Is it okay with all of you? Is it okay? Yeah. So
yes, sir.
So how will the frequency response will be like? Like it is good. Pointer options. Yeah. Oh, sorry. Okay, it will go like this. Okay, there are two poles, right? So first pole will come here. It will 20 dB per decade. It will start falling, and then 40 dB per decade. It will start now falling after that. So there will be two poles out here, right? So although the bandwidth will be defined like this, but if you see in more detail, this is how the response will be there here. So at the first pole, okay, the first pole will be, right, which will be the first pole, this, right, CGD into gain into RS, okay. So this will be the first pole, this much, right. So this first pole will be encountered here. So that will define me the highest frequency which this circuit, because this has got this is a much bigger capacitance. So that will start attenuating faster. So at that frequency, omega is equal to 1 by CGD into the gain into RS. Okay, this will be that frequency. When I reach that particular frequency, the gain will be 1 by 2. The power gain will be 1 by 2. Okay, and from there onwards, 20 dB per decade, the gain will start dropping. And then when I come to the second pole will be given by simply RS into CGS. Okay, RS into CGS. This. From there onwards, it will drop at 40 dB per decade. Is this understood? How this frequency response of this amplifier works?
Sir,
Yeah.
you have mentioned like you will clear the 20 and 40 thing. So now is it possible, or at the end you will clear?
No. What do you want to know?
Sir, as we discussed, like you mentioned, like after one pole, we will have a 20 dB decade.
Yes.
Then after second pole, there will be 40 dB. So my question was like after each pole 20 will be added, or like previous RC effect will be added in the output of the second pole.
Yeah. Yes. Actually, if you see, where does that 20 come from? Right. Power gain 20. How does that 20 dB come? Is right. Here, okay. So now here AV, if no, W by W0 here, from here. So for every decade, okay, I'll give you a link where I have given the that is in basic electrical science course. Where did that minus 20 dB per decade come? So that derivation part I will give you. I will share a link. Okay, you can go through that video. Okay.
Yeah.
Yeah.
No, sir, but doubt was actually like, can you go to next image? Yeah. This one.
Yes.
Yeah.
Yes.
So the question was like after first pole, the decade is minus 20 dB. So for that you will share the link. But my question is after second pole, why it become minus 40?
Because
so,
it is two filters, right? It is kind of when the second pole comes, okay, that is not applicable here in this particular circuit. Oh, sorry. So okay, yeah, nice, you brought this aspect. Here these two together, they are forming a single pole only, because these two capacitors can be considered as in parallel. Okay, so there could be one more capacitor and one more LC filter, okay, in the circuit. Like we'll see other circuits in which there could be multiple capacitance. So these two capacitors, so they come in parallel here, so they will form a single pole. But there could be other capacitors. So it is like one filter coming in series with other filter, right? So one filter, like suppose this is R C, okay. When the signal is going from here to here, this signal, if it was 1 here, okay, so it will get attenuated by 1 by root 2 times, okay, the magnitude. Again you have one more filter coming in the circuit, okay, the signal will again get from here to here, it will get again attenuated, so it will go to 1 by 2 now, right? So if you have multiple poles, every time the signal will get attenuated, correct?
So
that is
the now this pole will decide like minus 40 dB is applicable to which frequency range?
Yes.
Okay,
As you keep increasing the number of poles, okay, when two poles they start acting together, then that slope will increase. Because
correct.
Both of them will start. So initially, okay, the frequency is so low that you have not reached this particular frequency. So this is just bypassing it. But as the frequency increases, this also comes into operation now. Right? So the signal is getting attenuated 2 times.
Correct.
Okay, so that is why the slope keeps increasing. Okay, so this is about the high frequency, right? Okay, okay. The third option available is, okay, just put these capacitances and write the KVL KCL equation and try to find out the gain. Okay, so now if you see here, this is the voltage which is applied here. What will be the current? This will be V source divided by RS plus this current. Okay, that will be, this is the first current. This current is flowing here. This current is flowing here, right? Plus CS VGS into VGS, because the current in the capacitor is what? S into CGS into VGS. Okay, so this is the current which is flowing here, and what is the current which is flowing here? Okay, so we write V0. This is VGS and this is V0. So VGS minus V0, that is the voltage across the capacitance, into S into GD. Okay, so the current in a capacitor is known, right? You all know this, right? S into C into V. This is the current, right? Is it understood by all of you? Current.
Sir, you are replacing capacitor with its Laplace transform, or
yes.
SC.
Yes, that's a Laplace transform. S is a Laplace transform, right? Or J omega, whatever you write, right? So now, so these are the current. So now you write this current is 1, 2, 3 currents. You write these 3 equations, right? And also we have a V0 as GM into RL dash, right? So V0 also you substitute as V0. You substitute as GM into RL. So again, all these things get cancelled, and you have this gain equation coming. So this is without doing Miller effect or without taking each pole. You just write the simple equation of this network. Okay, by putting CD GD, writing the current equation, and you get the gain equation here, right? Again, this gain equation is equivalent to what we did there. So this is S square. So this actually can be neglected. If you neglect this term, this is what we got in our earlier case also, right? So it is almost the same. So these are the 3 techniques which are available. So the simplest one is this. Yeah, tell me.
So in this, why we have taken it as a current source, as CMOS is a voltage
controlled source.
This
is GM VGS, right?
Yes, sir.
So it is a current source only. Input side we
are but voltage controlled, right?
Yes. So GM into VGS. Okay. This symbol you say it is representing an current controlled current source, is it?
No, sir. On input side, input side we are taking.
It is just a representation of a voltage and a current. Okay. So we are just writing V in and I in. VI. Okay. Don't take too much into the symbol aspect. Okay. So this is the third option available with us. Okay. So the best option as seen will be use the Miller capacitance option. So that will be the easiest way and simplest way to get into the poles. Okay. So now if you see a circuit like this, okay, there will be several filters. Okay. So this could be one. This is for BJT. The same thing will be applicable to the MOSFET also. Here there will be one capacitance and a resistance. Okay, this will act like a low pass filter or a high pass filter.
High pass filter.
High pass filter. Okay.
High pass filter.
Okay. So this also will become an high pass filter. This will also prevent low signals to go. So there will be one more, okay, omega RC you can find out, and this also is an high pass filter, right? Because at low frequencies this will the gain will get disturbed. So this capacitance has to be high enough to trans. So there are three different poles out here. So this is 1, 2 and 3. Okay, so the placement of these poles will depend on that value, RC value. So these are the three poles in the input side. At the output side, there could be this capacitance which is coming, right, and this capacitance, right. So these are the two poles which comes in the output side, right. So what are the capacitance which will affect your low frequency operations and high frequency operations? You should be, so this capacitance, this one, this capacitance, and this capacitance, okay, they affect the low frequency operations. Okay, so these three, so each has got a resistance to so this capacitance is going to see this R1 and R2 in parallel, right, for a MOSFET. Similarly, this capacitance is going to see this source resistance and the impedance as seen into this node also. So that will be 1 by GM. Similarly, this capacitance will see this capacitance, it will see R0 here and it will see some RL here. So that will become, so all these RC combinations, that each one of them will give one pole out here. So that will here, okay, they will all will start attenuating the signals at the lower side. On the high frequency side, this capacitance is there and this capacitance is there, right. So they are going to do this at high frequencies. Is it okay with all of you? Okay. So,
Sir,
yeah.
Sir, as you mentioned, like the component which is seen in discrete form, that will affect our low frequency. But how we can say, is there any is there any method through which we can say this will only affect input side, low frequency side?
Because this is an when you see from here, there is a capacitor and a resistance here. So this is a low pass high pass filter, right?
Okay.
So you have to view it that way. So this capacitance, when I am interested at this voltage, this capacitance and this resistance, they will form again an high pass filter.
Okay, so this CGD and CGS will be low pass filter.
Yeah, they will be low pass filters. Yes, they will work as a low pass filters.
Okay.
Right. So similarly, if I have to find out the frequency response of an CG amplifier, okay. Now I am applying an signal voltage signal out here, right. So this is RS, this is an CS, which is the capacitance of the source of this transistor. So I have an CS out here, this is CGD, right. So this CS is actually sum of CGS from the capacitance from here to here and the source to body here. So this is CS. Okay, so now I have put a voltage source here. I am giving a bias voltage. At this node also there will be one CGD. So there are two capacitances. Okay. Now what is the thing which will be seen by each of these capacitance? So for the first capacitance, okay. So just क्लास चल रहा है, बोल दो जल्दी बोलो, पता नहीं यार कहीं से भी ला करे, क्लास चल रहा है, क्या रोटी मिलेगी, रोटी कहीं से भी ला, पकवान में मिलेगा, हाँ यापराल में, अरे वो पंजाबी दारू से Yeah, okay. So there are two capacitors. So let's see now what is the resistance as seen by this capacitance. Okay. So now if I put a voltage source here, right, test signal here. Okay. So one resistance will be Rs, correct? And what is the other current which will flow here? It will be GM plus GB into what is the voltage which is applied here, right? This will be ground here. So this current will be what? GM times V test, right? Plus, because there is a body effect, GM plus GB. Is this okay? Is this equation clear to all of you? If you have any doubt, ask me. See, I am putting a test signal instead of VCS. Okay, I am keeping this open. I am putting a test signal here. When I am putting a test signal, what is the currents which will flow? One is V test divided by Rs here, and one current will flow towards the top. What is that current? Okay, if I make the equivalent circuit here, it will be GM plus GMB, like, because there is a body effect also into this voltage out here. So since this is AC ground here, I am applying a test signal here. This will be GM plus GM into V test only. So now if I write V test by, so this is the impedance as seen by CS. So that will be one pole. Is it okay with all of you? Is it okay? Can I get some response? Yeah, okay. So similarly, what about the impedance as seen by CGD? Okay. Now this is CGD, right? So now I am going to put an test signal out there, right? And then I am going to see. So one is RD as, okay, and the other one, if I look from the top, it will be R0. It will be much greater than RD, so I can just say it is RD. So the second pole will be CD into RD. Okay, the first one will be multiplied by CS. CS into the resistance which was seen was this. Okay, so this. So this is. So now if you see here, these are the two poles which are corresponding to the CG amplifier. Okay. Now you will find that since this value, this will have much higher frequency, because there is no Miller effect out here.
Sir, excuse me, sir.
Yeah.
Sir, you said that there is a resistance in RO, right?
Pardon?
Resistance RO. It is because of we are giving the constant bias voltage at gate.
Yes, yes. So when I am looking from the top, okay, it will be an R0 when I look into the bottom.
Okay, actually that one I did not understand, sir. Oh, because of the bias voltage, or?
Yeah, because this is if the fixed, for a fixed bias voltage, like we saw when you look into, and it will be like a constant current source, and R0 will be the resistance in that case.
Then conductance will become GM.
When you are looking from the bottom, okay, because gate source voltage will get modulated by the applying voltage, it will be 1 by GM. But when I am looking from the top, gate to source voltage is fixed. So it will be like a constant current source. So it will be R0 when I am looking from the top.
And the conductance will also be GM, only GM, not 1 by GM. Because of the constant bias voltage.
No,
from the top.
From the top, it is just the resistance R0, which I am neglecting.
Okay.
As compared to R0. You don't have to bother. It will be R0, nothing to do with GM. And I am looking from the top.
Okay, sir. Then from the bottom, when we see with respect to source and the gate, that time it is only GM, right? It is still this constant bias voltage will be at the gate, right?
No, but gate to source voltage will change, right? Gate to source, that derivation we did, right? The impedance as seen into the source of a transistor, okay, will be 1 by GM plus GMB or 1 by GM. That we saw in our earlier class, right? This impedance, that derivation also we did.
Yes, sir. Actually, it is not clear, but here you have written only GM into GM plus GMB.
It is 1 by GM, but the more accurate equation will be 1 by
no, the first equation. In the first equation.
GM plus GMB.
Yeah, but you said it is 1 by GM, so it is only GM plus DM,
Right,
right?
1 by GM is the impedance, right? Current will be, right, the current will be voltage into V equal to IR, so 1 by GM, so that GM will come on top, right?
V divided by GM.
Correct?
No, V into GM.
Yes, V into GM.
Yes, sir. Okay, sir.
Is it okay? This current source.
Actually, still that GM is not clear to me.
See,
Like when we get GM and when we get 1 by GM.
no, 1 by GM is the resistance.
Oh, yes, sir. Like sometimes you are getting GM, sometimes you are getting 1 by GM. So I'm not getting that.
No, when I'm talking about resistance, I call it as GM. Okay, when I talk about the current, okay, V equal to I into R.
Not the equation, sir. Like when we see with respect to from you said from down like source and plate, and from the top like you said R naught and 1 by GM, right? That one I'm not.
Okay,
When you give the constant bias voltage.
okay. I think there's a noise from your side. Can you just mute your mic? Yeah. So this we discussed earlier. Okay, when you have an circuit like this, when you are looking into the source out here, okay, the impedance will be 1 by GM, right? But if you have an when you are so whenever this particular whenever you have an fixed voltage between the gate and the source, then when you see from your drain side, then it will be R0. So this derivation also we did for one particular circuit. Do you recall it now?
Sir, like can you go to the second one, like previous slide? Then the previous slide also it should be like how it is 1 by GM, sir?
This one GM. This is
Not
about
the second one.
here.
Yeah, that should be GM only.
No, the impedance is 1 by GM. As seen.
That's an NMOS.
Huh?
That's an NMOS. That's an NMOS. But the other side we are looking at the PMOS. That's why it's R0. I think the confusion is between the second and the fourth circuits.
Okay, this is a PMOS where gate to source voltage is fixed. So that becomes a constant current source. Right? And then we are looking into it, it becomes R0.
Okay, sir. Okay, that difference I did not notice. The NMOS difference. Yes.
Okay, so this is often CG amplifier. So these are the two frequencies. It doesn't have Miller effect. So obviously CG amplifier is it will have an higher bandwidth. Okay, so just give me. Okay, is it okay till here? Those two amplifiers. This is the third amplifier. this is about source follower. Okay, here source follower we saw it, it is also known as common drain amplifier. Here this is the load. Okay, now in case the load is CL, okay, what are the various poles? So you can do a similar analysis out here also, right? So you can this is writing an equation, right? And this V out is nothing but this current equation out here at this node, V out into CL into S. Okay, this is the Laplace equation. This is the current which is flowing into the capacitance. That is this current equation and the current which is going to flow out here. Okay, so this is sum total of this. So this is GM into V1, and this current is an V out into CL. This is GM into V1, and this current is V out is here, and here it is an V1. Okay, so V1. So this voltage we are assuming it is V1. So you get one equation between V1 and V out. And from here, if I write one more equation, it is a V in, that is I into RS. Okay, that is one current, and into this voltage, right? Here it is again you have to find out the voltage across CGS. To find out the voltage across CGS, this voltage is available here as V1, and this is available as V out. So you write that equation out here. So you solving these two equations, you will get V out by V in here. So doing these things also, and you get the pole for this particular circuit also out here. So these are the ways you can find out various poles from these circuits. Okay, so here also you will find that this doesn't suffer from very high frequency issues. Okay, so all those things, these circuits might you don't have to really worry about the takeaway from this particular lecture should be only a few things, that for a CS amplifier, the CGD, okay, comes into the input side along with an Miller effect. Okay, that is that the CGD gets multiplied by the gain factor, and hence it suffers from a high frequency attenuation. It has got a lower bandwidth. Okay, whereas the analysis of a CG amplifier, okay, you will find that it doesn't suffer from that kind of Miller effect. So it has got a much better bandwidth. Okay, as compared to the CS amplifier. Okay. So the only problem with the CG amplifier, it has got a low input impedance. Okay, so these are the things, takeaway points from here. Okay, so you need not worry about any numericals from this particular lecture. So just the basic concepts you have to remember. Similarly, for an source amplifier also, if you see the analysis out here, so it doesn't have a serious frequency attenuation issue. Okay, so these are the things which you need to remember. Okay, so now
sir,
yeah,
sir, from that equation, how have you analyzed it will not affect high frequency?
If you see here CGD, okay, and then if you divide by GM, okay, one pole is at RS into CGD, right? The other one is CL divided by GM and CGS divided by GM. Okay, whereas here, so you will find they are all not getting, they are all that they will land up at much higher range, right?
So denominator become very low. So
yes,
numerator will be very
high. Correct, right? Whereas for the CS amplifier, this CGD is getting multiplied by the gain. Correct? So,
correct.
Yes, so that is the issue. So this becomes very high in that case, and hence this frequency will become low. So the bandwidth available is lower. Okay, so that is the way we analyze. Okay. So You can just
Sir, like, can you
yeah.
go to the previous slides?
Huh.
Like, you said 20 dB, 40 dB, and the third one was 20 dB again. It should be 60 dB, no, sir?
60 dB, yes, 20, 40, 60.
But it was 20 only.
Where?
Here.
Okay. No, I just paste one. This can be 20 dB in case there is an 0 which is coming onto the numerator, right? So it can offset the this minus 50. It can have a plus 20 dB. So these are the two poles. If a 0 comes here, okay, for when you write the transfer function, okay, if a 0 comes here, then this will go into minus 20. Okay.
So this one you are
right. So here when we wrote these things, generally that 0 comes at very, very high frequencies. If you see here, when we did one analysis out here, so there is an 0 also on in the numerator, right? So that 0 out here. So so if you consider this particular expression, those zeros can push this again towards the up.
So that means we have to consider for CGS or CGD, sir?
Pardon?
CGS or CGD we have to consider?
No, that once you write here in this particular equation, you will find it is CGD along with GM. Okay. So once you write the expression, then you will come to know what is the one which is coming in the numerators. Okay. So basically those are working in analog design at high frequencies. So you should know what are the components which will affect your high frequency operations. Okay. Yeah. Tell me.
Sir, you mentioned you will share one video in which the effect of poles will be explained. So as you mentioned, the effect of 0 will be, it will improve our that thing by plus 20 dB.
Yes.
So is that also explained in that?
No. This should be coming in some control systems or electrical. That was an
okay. So
okay. You'll have to search for it. Okay.
Okay, sure.
Okay. So this is of an CG amplifier. Right now, if I talk about an cascode amplifier, okay, again there are several capacitances here. One capacitance here, one here, one here, one here. Now, if I talk about at each node, okay, at node A, okay, CGS. Now, if I have to find out what is the thing which is coming along with CGS, okay, I put an open circuit here. CGD goes. So CGS is with RS, okay. So that is one. So the CGS will see RS. So CGS RS, okay, that is taken care of. Now what about CGD? Now for CGD I remove this. Okay, what is CGD going to see? It is going to see RS, okay, and it is going to see here like this. But this capacitance we are going to keep it open, and it is going to see here, and it is going to see here. Okay. So now if you see here, so when I am going to see into the top, it is going. When I am going to see from here, it will be 1 by GM. So that GM comes into CGD, right? And similarly, when I am going to look into this, okay. So there will be GM2 plus GM. So this capacitance is going to see. Okay, these are the impedances. So you club this. So this is one pole which is coming at this particular node. Similarly, if I take this X node, okay, this is the second node. So at this node also I have one capacitance here, okay, and what is the impedance as seen by this capacitance? One is a GM plus GM2 which is seen here, right, and towards the bottom I have this capacitance also. So that will also is going to see the same impedance, okay, this. So I club all these two capacitances and I get the pole at this particular node. Similarly, there is a third node out here. Okay, and at that third node, what are the capacitance? One is this CBD2 and CL and CGD, and the resistance as seen will be RD. So if you see towards the bottom, it will be R0, which is much higher. So I'll just take an RD there. So these are the three poles which are associated with this particular cascode amplifier. Again, you will see all these things, and there will be no Miller effect out here. So they will not really cause. So RS into CGS and RS into CGD. So they are the ones which will determine the dominant pole. Okay, so this is about cascode amplifier. Okay.
So one query. How we have divided the resistance for M1 for CGD1?
So
how
when you,
I understood for M2.
When you look into here, right? If you are applying a voltage out here, right? Even the gate source voltage is getting modulated, right? So and that is why it is coming as GM1.
Okay, sir.
Okay. So you have to apply a test voltage here and find out the test currents which is going to flow, right? So this current out here which will be flowing, okay, test current will be GM times the voltage, and hence it will come as an GM into C1, right? Whereas I am looking into the top out here, right? So it will be 1 by GM for this particular. So you have to keep removing each capacitance and apply the these things. Okay. So
okay.
These are the voltages out here. Okay. Now frequency response of an differential amplifier. Yeah. Tell me.
Sir, one doubt.
Yeah.
Can you go to please back side?
Yeah.
Sir, here for the omega px, you have considered from the at x point looking towards M2 that you have considered GM2.
Yes.
But when we look into M1,
yes,
that we don't need to consider.
Yeah, that is a much higher resistance as compared to GM. So that is why we are neglecting that.
Sorry, sir.
That will be R0, right? When you look into M1, okay, from node X, it will be R0. That voltage will be much higher. Since R0 is much higher as compared to 1 by GM, so we are neglecting that.
So, but here we are not considering then R0.
Yeah, that's what. When I'm talking about node X, when I am looking from top to bottom, okay, the impedance seen will be R0.
But it should be, sir, 1 by, should be GM plus 1 by R0.
Yes. So, no, the impedance will be R0 when I am looking from the top, and R0 is much higher.
But sir, here VGS is not constant.
No,
then how we can remove the effect of 1 by GM?
No, VGS is constant, right? Because I am talking about this. I am going to remove this CGD, right? I am talking about X node, right? So for each, when I am talking about CGS, I am going to put a voltage source there and remove a CGD1. Then when I look from top to bottom, it will be only right, only the drain to source voltage, and the gate voltage will be fixed there. Correct?
But sir, normally when we create that small signal circuit, in that case we are removing the DC sources, not the input AC sources.
No, input AC source will, no, when we are talking about the equivalent resistance as seen by a capacitance, in that analysis, we remove the sources also, AC sources also, and remove the other capacitances also.
Okay.
Right, and then see. So when I see from the top, when I'm talking about CGS2, CGD will be removed. So from top, right. Similarly, when I'm talking about this, the other resistances will be removed. Other capacitances will be removed. So it will look like an
So when we look towards M1, so it will be 1 by R0. So that then
yes,
so we are neglecting
we
it.
are neglecting that.
Okay.
So when we come to frequency response of a differential amplifier, okay. So this differential amplifier, it is similar to that of common source voltage. Okay, this also suffers from a Miller effect. So because this capacitance, okay, from here to here, okay, that will get multiplied by the gain, right? So same issue, whatever is the problem which we encountered for an CS amplifier, the same Miller effect gets can be seen in a differential amplifier also, because this is actually a CS amplifier only, right? It just has got two sides of it. So this also has got an same issue with frequency, right? So but for the common common mode signal, okay, this was the equation RD by 2, if you remember, 2gm plus 1 by, this is the common mode formula out here, right? Now in this case the RS is getting modified as parallel of R03 and CP, right? They are going to be in parallel. Okay, now this CP is seeing, this is the capacitance of this particular current source. Okay, it is seeing two resistance, one is R03, the other one is the capacitance as seen into M1 and M2, another resistance. Okay, so R03 and then this GM plus GM2. So this capacitance is seeing two particular resistances. One is R0 and one is 2GM3, right? So this capacitance. So now you will find there are two poles out here. So at high frequencies, okay, so they are going to deteriorate your it is going to cause higher common mode gain, okay, because this resistance is actually decreasing the common mode gain, right? But this capacitance, if there is a capacitance at higher frequency, the common mode gain will increase and hence the common mode rejection ratio will decrease. Okay, common mode gain will increase and the differential gain will decrease, common mode gain will increase. So your CMM, common mode rejection ratio will decrease, okay, with increased frequency. So that is what happens with differential amplifier. Is it okay with all of you? So you have
Sir,
yeah, tell me.
Sir, this equation second AVCM you have written, how it is coming? Can you explain it again?
This is like what we have done is the this is the equation which you, if you remember, this was the common mode gain equation. Now RD is in parallel with CL here, so RD is parallel with CL.
Okay.
Okay. Now RS is nothing but R0 in parallel to CP.
Okay.
So that has been put like this.
Okay. 2GM. Yes.
Right. This was an approximation which was done. It is actually GM plus GM assuming both to be the same. Okay, so here it is written separately.
Sir, here how delta GM, like why delta GM is mentioned?
I think that was taking into consideration in case both the GMs are also slightly different. Okay. This analysis also we did.
Yeah.
Okay. So that is also incorporated here. So this is what happens in case. So you the takeaways should be important. Okay. So in this particular chapter, we will not worry too much about any of these derivations. Okay. Only just the concept. Okay. So it's not, this chapter may not be important from your exam point of view. The concepts should be clear at what happens at high frequencies. Okay, all these capacitors and how do they deteriorate your gain. Okay, so that is all important. So let me show you some simulations so that what we learned will become clear. So to start with, let me this was an assignment about a folded cascode. Okay, so if you see here, this is an 5 milli, and if I see the output, okay, this is an AC analysis. So let me do an transient analysis. Right, so I am getting very high gain, around now 120, right? So very high gain. So how did I achieve this high gain? By ensure I have put an 500 microcurrent here. So let me revert back my mouse size. Right. So this 500 microampere. So unless you ensure that these two transistors are in saturation and sufficient current is flowing in these two in the folded cascode, you will not get a good results. So if I plot these currents, if you see here, right? So these currents are what? 330 micro and 60 micro. 330 micro is in M1 and 60 micro is in M2. Now if you see here, what is the gain of this folded cascode? GM into GM of this transistor, right? And R0 of this transistor. So I have to keep a GM of this transistor large. So among the 500, around 360 I am putting it into this transistor, and I have to put some reasonable current here also. So I am keeping it at around 150. So high current here, lower current here. But both these transistors are in saturation also, and that is the reason you will find I am getting a very high gain out here. And see, you see 330 is the current there, 60 is the current in the other side out here. So this is how you design a folded cascode. So most of you have done it in your assignment, but the gains are much lesser, and many of you have not ensured that proper current is flowing in both the branches. Okay, so if you ensure that the currents are there is adequate currents in both the branches, and then if both the transistors are in saturation, then you will get a very high gain. Okay.
Sir, one down.
So what is the W by L ratio?
W, I think there are 20 microwatt. Okay, each of these transistors.
So can we do once the DC analysis for this folded? So can we perform DC analysis for this folded Cascode amplifier?
Yeah, you can do a DC analysis, or you can do a transient analysis and plot the voltages available here, right? So the okay, this again are doing AC analysis.
So actually, I just want to see the waveforms, how we are getting for the DC analysis.
No, for a DC analysis, you have to sweep some DC voltage, right? So it is better to do an transient analysis and then plot those voltages. So transient analysis will give the DC operating conditions also, right? So this is the DC operating condition out here. What is the voltage if you see here? It is 600, 600, around 600, right? So this transistor will be on. If I take the voltage out here, it is 1.53. So obviously this is in saturation. If you see the voltage out here, it is around 0.9 volts. So that is above the threshold voltage. So this is also in saturation. So that is how you can undo the DC operating conditions at various places. Okay. So you find the DC operating point.
Sir.
Yeah.
For M1 and M2, we need to keep their GM values equal, so that that GM into 1 by GM we can cancel out.
No.
But sir, as we discussed in
for folded
Cascode,
no, in the Cascode, if you remember, okay,
Cascode for good frequency response, we don't need any gain from input of gate to the M1 of drain. So for that we need to keep GM into 1 by GM.
Yeah.
So in order to cancel that, we want our GM1 should be equals to GM2. But here both currents are going different in the branches.
Yes. No, that there will be a small difference in the frequency, but otherwise if you see the gain equation, right, it is only GM1. Correct? So for achieving a higher gain and bandwidth will always be trade-offs. Right? But if you want a higher gain, you can afford to keep. Okay, but that will not affect too much. Okay, gain is a major issue out here. You will be looking, right. As such, it doesn't suffer from any Miller effect. Okay, so that a small loss in gain is acceptable out here in this case. Okay, so now if I talk about an CS amplifier, right? If I put 1000 micro out here, and if I do an analysis, so right, so this is what I get, right? So this is 1 kilohertz. Now if I instead of this 1000, if I reduce it to, so I am sweeping only till 1 kilohertz. So at high frequency, that attenuation is not shown out here. So instead of that, if I reduce this capacitance and if I run it, then I will find it that it is attenuating even higher frequencies out here. So it is we have to ensure that these capacitances are high enough for our frequency to pass. Now if you see here, even 10 kilohertz is being passed. So that choice of this capacitor will enable me to see what frequency it is passing, right. Similarly, here I have just put it as 1K. If I put it as 1G, and then if I do a sweep, then I will find that at higher frequency, when it goes, this starts dropping out here. Okay. Now from 1 megahertz, it is from 100 to 1G, it is falling. So if you see the slope of this curve, it will be around 20, right, 20 dB per decade. It has to go like that. So you can verify that also. So that is how this is a high frequency. That is because of these capacitances, right? At lower frequencies, this capacitance is going to do the attenuation. So I can show you one more circuit.
So what does this dotted line shows?
That is phase.
Okay.
That's the phase. Okay. So here I have put only 1 micro. So there will be some low frequencies which will get attenuated out here, right? So now see here, right? So this is an at low frequencies. Now I told this low frequencies, if I put this as 1000, so in the design you have to cater for that. If I put 1000 instead of this 1000 here, and if I run it, so low frequencies are now able to pass here. Now even this capacitance can cause an issue for low, right? So if I put this 1 micro here, if I run it, see again it is causing an issue at the low frequencies, right? So even the third capacitance out here. So these are all external capacitances. So these are all we have to take care on in design. So if I run here again, so this is not making much of a difference. So probably because these resistances are very high. So but if I further decrease it, it start going to make a difference. So these three capacitances, as you see in these simulations, will make an effect at the low frequencies. At the high frequencies, what is going to make effect is the parasitic capacitance of this transistor. Okay. Now these parasitic capacitance of this, we can't adjust that, right? that is not in our hands. That comes from the size of these transistors. And now the size of those transistors are dependent on the gain and other parameters. Since we have seen the design steps, so the size of the capacitances of those, the capacitances which parasitic capacitances which come into play because of the size of the capacitance, the transistors is not within our hands. So we generally change the topology in case we want an high frequency amplifier. Instead of going for a CS amplifier, we might go for a Cascode amplifier or a CG amplifier. So that way, okay. So only the low frequency capacitances we take into consideration, okay. Otherwise, if you have to increase the bandwidth, that we will see in the when we learn about the multi-stage amplifiers, we will compromise, we'll have a kind of negative feedback, and we'll compromise on the gain and increase the bandwidth. So that is other options which are available with us, which we will see in the subsequent classes, okay.